In this lesson, we'll be learning about the intermolecular forces. First of all, what are they? Intermolecular forces are the attractions between molecules. So let's go over what we know. For ionic compounds, there's a metal and a nonmetal involved. The metal gives its electron to the nonmetal, creating ions. And the reason that they are attracted together is because of their strong electrostatic attractions. But today, we're only talking about intermolecular forces. And ionic compounds are not molecules. So there are no ionic compounds involved in intermolecular forces. On the contrary, how are molecular compounds structured? Well, pretty similarly, it involves some moving of electrons. However, molecular compounds only have nonmetals, and the electrons are shared rather than fully transferred. Take this water molecule for example. The oxygen atom has a bond to each of these hydrogen atoms. Are these bonds intermolecular forces? No, it is something different. These are intramolecular forces, the forces of attraction within a molecule. Just for a reminder, intermolecular forces are the attractions between molecules. So let's say we had a second water molecule. The way that these two would be attracted to each other is due to their localized positive and negative charges. We're going to pause right here. If you are not strong in the area of polarity, I recommend checking out my lesson on electronegativity and determining polarity as something you should watch now and come back to this video later. But anyways, because the positive hydrogen ends of this water molecule is next to the negative oxygen end of this water molecule, this is where we see our first intermolecular force of attraction. Now in comparison, these intermolecular forces are relatively weak compared to the intramolecular forces, which are these covalent bonds within the molecule. To put this into an analogy, think of the bonds between the oxygen and hydrogens as the bonds that you have in relationships with maybe your parents, your siblings, grandparents, other close relatives, or close friends. While these intermolecular forces represent the attractions and bonds that you have with your school friends or work friends. You may bond in that environment, but you wouldn't really hang out in real life after school or work. Hence why that relationship is not as strong as ones with your close family and friends. So keep that in mind when you're comparing the two. Specifically, this intermolecular force is known as the dipole-dipole force of attraction. And simply, these dipole-dipole forces are the attractions between the oppositely charged ends of polar molecules. A great way to show these intermolecular forces in action is, let's say we had a faucet with running water. On the molecular level, all of the water molecules would just be falling down into the sink bowl due to gravity. Nothing to do with intermolecular forces. But let's say we had a metal stick or rod that we rubbed with a cloth or a towel, causing it to become negatively charged with electrons. If we took this metal rod and moved it towards the running water from the faucet, it shouldn't take long for just one of the positive charged side of the molecules to be attracted to this negative charge. If these attractions do occur, then that would open the door to even more attractions. Because with this molecule having its negative polar end facing a positive end of another water molecule, and so on, eventually all these attractions would lead to bending the stream of the water. And this is all due to the dipole-dipole forces. Pretty cool, right? Now these dipole-dipole forces can occur for any polar molecule. So say we had maybe hydrogen chloride, HCl. Hydrogen has a 2.2 electronegativity and chlorine has a 3.2 electronegativity. The difference is only 1. So this is a polar molecule, and so this chlorine will have a slightly negative charge and this hydrogen end will have a slightly positive charge. Let's say we had more than one of these molecules. If they were around each other, the positive hydrogen end of this hydrogen chloride molecule will be attracted to this negative chlorine end of this hydrogen chloride molecule. And the other way around, which can apply to all polar molecules. But what if a molecule is not polar, and we had a gas like O2, which is a molecule made up of two of the same atom, meaning that they have the same electron negativity, meaning an equal sharing in electrons, meaning no localized positive and negative charges, and no polar ends, so this is a non-polar molecule and cannot have dipole-dipole forces. But does this mean it doesn't have any intermolecular forces? Well, they actually do, but it is a very weak intermolecular force, called the London dispersion force, or the LDF. Taking a look at this oxygen gas molecule. Obviously, we have the two oxygen atoms with these two bonds holding them together, and we have these other valence electrons that we rest on the corners of the oxygen atoms. This is good for a rough sketch of the molecule. However, the electrons are always going to be moving and scattered all over the place. So let's forget about the rest of the molecule and just look at the electrons. Let's say these two circles represented the inside of the molecule, and the electrons are constantly moving. If they are constantly moving, then that means we can assume that at one point, all of the electrons on this oxygen molecule has all of its electrons on the left side of the molecule. Assuming the left oxygen molecule has the same electron configuration, where both sides only have their electrons on the left, this actually creates temporary polar charges on the molecule. Obviously, the side with the electrons will be the negative side, and the side with the absence of electrons will be the positive side, creating a force of attraction. However, we have to remember one key part of information, and that is that these electrons are always going to be on the move. So realistically, the electrons will only have this specific configuration for maybe not more than a fraction of a second, meaning that these attractions are indeed possible, but they're only temporary and rarely occur. And now, moving on to the third and final intermolecular force. This can be classified as just a stronger dipole-dipole force. Let me explain. So of course we know that in order for a dipole-dipole force of attraction, there need to be two polar molecules which have ends that are attracted to each other. And in order for a molecule to be polar, its electron negativity difference has to be between 0 and 1.7. With this range, we can only assume that the larger that this difference becomes, the more polar that a molecule becomes. Seeing as compounds with electron negativities of 1.7 and greater are ionic compounds, which have nonmetals that completely strip the electron away from a metal. And so the molecules that are highly polar have more distinct and stronger charges. Three elements, including nitrogen, oxygen, and fluorine, are three special elements, seeing as they have three of the highest electron negativities on the periodic table, meaning that when in compounds with other atoms, they have the highest strength for bonding electrons. And doing the math, it would only make sense that they have a very high electron negativity difference. Now, so far, nothing new has really been said. Yes, anyone thinking logically would think that elements with high electron negativities would be more polar and they would have more distinct and stronger charges. But there's one more key phenomenon that occurs, and that is when dipole-dipole forces of attractions occur between any molecule containing one of these three elements with a hydrogen end of a molecule. Let's take water, for example. If we have many water molecules that form dipole-dipole attractions with each other, it would be because the negative oxygen end is attracted to the positive hydrogen end. Now, of course, through normal dipole-dipole forces, the positive and negative charges are enough to keep them attracted to each other. But because oxygen formed the dipole with hydrogen specifically, this makes their bond a lot stronger than the ordinary dipole-dipole force, and results in outcomes that almost unexplainably give water and other molecules that have what's known as hydrogen bonding unusually strong properties. See, if we take a look At this graph, which represents boiling points, we can see that compounds like methane have a very low boiling point, but molecules like water, hydrogen fluoride, and ammonia have extremely high boiling points, deeming the attractions between their molecules to be a lot stronger than other molecules which have standard dipole forces of attraction. And it's important to note that these three compounds include hydrogen bonds between hydrogen and nitrogen, hydrogen and fluorine, and hydrogen and oxygen. Now, just to wrap things up, let's summarize what we've learned today by ranking each of these intermolecular forces from weakest to strongest. First, we have the London dispersion forces. Relatively, these forces are really weak. These attractions can only be formed if there's a specific electron configuration that only holds for fractions of a second. We can apply this force to nonpolar molecules, which are most of the time going to end up being gases. Then we have dipole-dipole forces, which are pretty strong compared to the London dispersion forces, as they are the attractions between the polar ends of molecules. These are generally the forces between gases and liquids. And then third and finally, we have hydrogen bonding, which is very strong compared to London dispersion forces, and also a stronger dipole force that creates unusually strong bonds between hydrogen ends of a molecule and nitrogen, oxygen, and fluorine ends of other molecules, including water, hydrogen fluoride, and ammonia. If you've made it this far into the video, chances are you're learning a lot and enjoy the content. So if you don't mind, consider subscribing, as it shows me that you like what you see, which helps me post more videos. Anyways, that's all for now. I hope you have a wonderful day.